In this video, we'll take a look at Bootstrap aggregation. Bootstrap aggregation, sometimes called bagging. So Bootstrap aggregation was introduced by Bryman, and it is a fantastic technique for taking a classifier and making it better. It basically takes an arbitrary classifier and by aggregating a bunch of sort of copies of that classifier, it can improve the performance. It doesn't always improve the performance, but many times it does. So it's very, very surprising. And it's very simple too. So here's the idea. In classification, let me make these random variables. So we've got some data set, and each of these xi's is a point in, say, d-dimensional real space or something, and the yi's, let's say, are, let's take the case of regression. Actually, we can apply this to both classification and regression. So let's think about regression first. So the yi's are some real values, and these are drawn, let's suppose they are drawn independently from some probability distribution p. So we've got our data set, and then, as usual, we get some new point. Let's make it a non-random point, say x, and we have to predict y, the y associated with that x. And I'll make that a random variable since it's going to depend on our data set. And it depends on our procedure, but let's fix our procedure, our algorithm, and then the y just depends on the data set. So we've got this set up, and let me just draw the picture. So we're thinking about regression. For example, just in a simple 1D case, maybe this is x and y-axis, and let's suppose we've got some data, some points. These points are, I don't know, maybe they're, well, let's make them blue. Something like this. Some points in our data set. And let's suppose that there is a true underlying function. For now, let's suppose that there is some function, f of x, which these are drawn. So we draw an x, maybe, who knows, maybe uniform or something on some interval, and then we draw a y. Maybe the y's are, say, I don't know, Gaussian distributed around this line or something like this. The intuition is, okay, and I have to draw our point. So we've got some point that we're asked about. Maybe it's here. So this is, let's make it yellow for consistency. So this is our point x that we have to predict a y for. The ideal y would just be the true value here. But we're going to predict some y, which is going to be a random quantity. So maybe for our procedure, for this data set, we end up predicting, say, that y. So the intuition behind Bootstrap aggregation is if we had a bunch of data sets, so let me redraw. So we got this curve. Oh, make it red. So we got the same curve, and each time we get a different data set now. Some other data set here, who knows, something like that. And each time we're predicting the same x. And maybe this time the y ends up, I don't know, so here. Maybe this time it's pretty close that time, something like that. So each of these is our random y that depends on the data set. And if you were to imagine that each of these data sets is independently drawn from P, then if this y is pretty good on average, maybe if its mean is the true value, then over time the intuition is that the average of the y's will be very close to the true y. Now, unfortunately, we can't, we only have our one data set, so we can't get all of these separate copies of data sets independently drawn. But in bagging and Bootstrap aggregation, what we do is we take our original data set and we approximate P by resampling. So what does that mean? That means, roughly speaking, we can make it more precise later, that we would draw endpoints. So the first point would be drawn uniformly from this set, and then we put the point back, and then we draw uniformly again. We put the point back, and we draw uniformly again. So we get n new points, and some of them may repeat the old points, and that's called sampling with replacement. So let's make that a little more precise. So let's call this our first copy of our data set, just to make this precise. And we get another copy. Next copy. Oh, so we get the copy 2. It looks the same. We get some sequence of copies. So now so I'm supposing for the moment this setup where we actually do get independent draws. So we'll assume for the moment that we get these. Let's call that M. We get these independent draws, and we'll use this to motivate the use of using bootstrapping. Xn, Yn. And each of these is independent data set. So for each of these, right, we had a y1 associated with that. We get some other y's. We get a y for each of them, and then we get a ym for the last one, all associated with the same value x. Now, let's suppose, to make life easy for the moment, let's suppose that each of these y's, I'll just say a generic one, we'll call it y, has mean equal to the true value. In this case, we have a true value here for our function that we're trying to estimate. So to make life easy, let's suppose that our estimator, in statistical language, that's what this is called, our estimator of y, or rather the function is called the estimator. This random variable then is called the estimator, and our estimator has the correct value as its mean, so that's called an unbiased estimator. So now let's think about if we were to measure our error, let's suppose we measure our error according to how far we are from, so that the squared distance from the true value. Suppose we measure it by this. Then the expected value of this quantity is called the risk. So this function is called the loss function, and the expected value is called the risk. And since this is equal to expected value of y by assumption, this is just the variance of y. So let's define a new random variable z that's a function of each of these separate y's. So this is where the aggregation comes in. So we will define z. So we'll define z to be the average. So we had, I said m of these y's, I from 1 to m. So it's just the average of the y's. So this is using this intuition. And now let's compute the error for this, or rather the risk for this z. So we have to take this thing. Now the expected value of z, oh, I didn't use my correct notation here. This should be superscript I. So the expected value of z, by linearity of expectation, this moves through, and we get the sum of the expected values. Each of the expected values by assumption is little y. So if we sum those all up, we get just, since there's m of them, we just get y. So z is also an unbiased estimator. So this is equal to the variance of z, right? And z is a sum, well, it's 1 over m times this sum. So using properties of variance, which you can easily check these properties. You just write out the definition of variance. So this is equal to 1 over m squared times the variance of the sum. And then, since these are each independent random variables, the variance of a sum of independent random variables, you can check, just write it down and use the fact that expected value of a product of independent random variables equals the product of their expectations. You can just check that. The variance is the sum of the variances. And each of them has this variance, or our generic y here. So it's just 1 over m times the variance of y. So now, note that, so this is our risk, our expected loss, and there's a very important observation here, 1 over m. So m was just a parameter that we chose, right? We said we'll take m copies, or we'll take m, give us m draws from our distribution, and our expected loss is 1 over m times the variance of our original estimator. So that means by taking m to infinity, that this expected loss is going to go to 0. Now, of course, in all of this, we've been assuming that we could get actually IID draws from the true distribution. But of course, we can't do that because we just have our one data set. So what do we do? So the intuition is that we approximate P. So approximate P by, let's call it P hat. So P hat is the empirical distribution. And we will draw, instead of these true samples, we'll draw bootstrap samples from P hat, the empirical distribution, just in the way that I described before. So the x, so for example, xik for some k, yik, this is drawn uniformly from our original data set. So D was our original data set here. We draw them uniformly from the original data set and IID. And that defines our bootstrap samples. So that's bootstrap aggregation.